Hey guys, we are doing exponential growth and decay, starting out in our unit on logarithms, unit 3. And what we've got here is about exponential functions. If it doubles every year, it can be modeled by an exponential function. And that would be 2, our growth, to the x, which is every year. We'll get that in the next slide. The parent function is f of x equals b to the x, where b is a constant and x is the independent variable. So the x here, the actual exponent, is the one that changes. Okay? The b stays the same. B to the 0, b to the 1. I guess I can put it here. B to the 0, b to the 1, and b squared. Okay? So that is an exponential growth. 1 over 2 to the x would actually be a decay because it's getting smaller and smaller and smaller. Okay. The graph 2 to the x. So here we go. 2 to the 0, which is 1. 0, 1. 2 to the 1, so you have the point 1, 2. 2 squared, so you have 2 to the 4, 2, 4 as your point. And 2 cubed would be 3, 8 as your point. On the other side, if you've got 2 to the negative 1, that is 1 over 2. The negative makes it flip, and so you would have 1/2. That would be 1 over 2 squared, which is how they get 1/4. And so it's getting smaller and smaller and smaller and closer to 0. Okay? In this a, b to the x, a is your initial amount. B is the constant of growth if that b is greater than 1. So that's where we got the 2 to the x. This is a growth. It's a constant of decay if that b is between 0 and 1. So that would be a constant of decay coming down like I had drawn originally. X is usually the time. Okay, so recall the transformations. We just did that in parent graphs. B to the x, if you put an a in front of it, it makes it stretch up like that or lay down a little bit more. Is a compression. Reflection, if it's negative, it would be reflected over the x-axis. Translations with the k and the h, this moves it left to right, opposite whatever that sign is. This moves it up or down, and it's exactly the same as whatever that k sign is. Those are the same parent transformations we did in the last unit. Okay. This is just listing it again, and this is reflecting across the y-axis, which you didn't do before, and that is what happens when you have the 2 is to a negative x up here instead of the negative being out front. It's across the y-axis if it's up top, it's the x-axis if it's out front. Okay, logarithmic graphs, just the graphs. It is an inverse of the exponential function. We'll get into that more on the next unit. But in terms of the graph, inverses always are across the line y equals x that goes straight through 0, 0, 1, 1, 2, 2, 3, 3, the identity function. And it reflects across there. You can kind of, if I tilt your head a little bit, you can see exactly. It's exactly a reflection across there. Okay. Your parent function is log base b of x. And here's how they move. A stretch out front would have an a in front. That would stretch it up farther. The compression would lay it down a little bit. Reflection would turn it over the x-axis. Translations, again, same thing as before. This moves it right to left, and it's the opposite sign. This moves it up or down, And it's the same sign if it's outside parentheses. Okay, so this is the one that I had on the other thing. It's a standard form of what you're looking for. And we can use it in Desmos, so that's always good. But you definitely need to get this down, what these all are. This B is going to be used, we've got another thing for it coming up. It is 1 plus the rate, or minus the rate. And that's how we end up with a constant of growth or decay in a little bit different form, but it's still the same B. Okay, X is usually the time still. All right, here is your exponential decay and exponential growth. As the value of X increases, okay, X is getting larger and larger and larger here. Y is getting larger and larger and larger here. Okay. For exponential decay, as the value of X is getting larger and larger and larger this way, your Y is getting closer and closer and closer to 0. It is not going to hit 0. The x-axis is an asymptote, like I told you before. But it is going to get close to 0, as close as it possibly can. Okay. So I'm going to stop here for 1. That's just basically what it is. And on the next video, we'll get into a little bit more detail.